On a clear night, far from any city, you can see it without a telescope, a band of pale light arching from one horizon to the other, faint, diffuse, almost ghostly. Ancient people saw it as a river, a road, spilled milk from a goddess. You are looking at the galaxy you live inside. You are seeing your home from the inside. But here is the thing. What you are actually seeing is almost nothing. The Milky Way contains somewhere between 200 billion and 400 billion stars. Let us use 300 billion as a working estimate. 300 billion individual suns, most of them far brighter than anything you could see from Earth. And when you look at that pale band overhead, when you look at the actual Milky Way, you are seeing approximately 1/10,000th of those stars. The rest are hidden by dust, by distance, by the sheer thickness of the disk you are embedded in. You see a suggestion, a smear, the light of a few hundred million, of 300 billion, compressed by distance and obscured by 200 light years of intervening gas and interstellar grains of carbon into that faint wash across the sky. The Milky Way looks like a gentle glow. It is one of the most violent, complex, and ancient structures in the universe. And to understand why those two descriptions can simultaneously be true, you need to understand the difference between what light shows you and what physics reveals. When you see the Milky Way, you are seeing visible light, photons, with wavelengths between roughly 400 and 700 nanometers, the narrow band to which human eyes evolved to be sensitive. Those photons can only travel to you from stars close enough and unobscured enough that their light reaches your eye without being absorbed by intervening dust. Most of the galaxy's stars are hidden behind one or more dust clouds at various distances, their light scattered and absorbed before it reaches you. But the galaxy is equally real at every wavelength of light. In radio wavelengths, the cold hydrogen gas that traces the spiral arms is clearly visible, mapped in detail by decades of radio telescope surveys. In infrared wavelengths, the dust that blocks your view becomes transparent, and the structure of the central bulge and bar becomes visible. In X-ray wavelengths, the hot gas in the galactic center region, heated by stellar winds, supernova remnants, and the vicinity of the black hole, glows brilliantly. In gamma-ray wavelengths, the Fermi bubbles dominate the view. Each wavelength reveals a different layer, and some of what constitutes the Milky Way emits no light at all. The dark matter halo, 5 to 6 times the mass of the visible galaxy, is invisible at every wavelength. It contributes no photons to the sky. It is known only by its gravity. Its existence was unknown to astronomers a century ago, suspected 50 years ago, and confirmed 30 years ago. Its nature remains entirely unknown today, despite being the dominant component of the galaxy by MESAS. What this means for how we think about our home is significant. The Milky Way you see, the pale band, the glow of billions of stars, is the luminous tip of a structure mostly made of something we cannot detect directly. Like an iceberg where the visible fraction above water is the smallest part. The galaxy is not primarily a collection of stars. It is primarily a dark matter halo in which stars happen to glow. The pale band you see is real, but it is the thinnest visible fraction of something far larger, stranger, and more ancient. The Milky Way looks like a gentle glow. It is one of the most violent, complex, and ancient structures in the universe, and most of it is completely invisible to you. So what does the galaxy actually look like? What is in it? How was it built? Where are we inside it? And what happens to it in the end? Those are the questions tonight. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let us start with the most important thing you need to know about the Milky Way, its size. Not a number, a derivation. Because the number alone means nothing until you build it from scratch and watch what it implies. The Milky Way is a disk. It has a diameter of roughly 100,000 light years and a thickness in the main disk of roughly 1,000 light years. But the disk is not uniform. It is thicker toward the center, where the bulge of old stars rises to roughly 10,000 light years above and below the plane, and thinner at the edges, where the spiral arms thin out into sparse populations of young stars and star-forming gas. 1 light year is approximately 9.5 trillion kilometers. 100,000 light years is therefore 100,000 times 9.5 trillion kilometers, which is 9.5 times 10 to the 17th power kilometers. That is 950,000 trillion kilometers. There is no human framework for that number, so let us find one. The fastest spacecraft ever launched from Earth is Voyager 1, which left our planet in 1977 and has been traveling ever since. It moves at roughly 17 kilometers per second. At that speed, crossing the diameter of the Milky Way, 100,000 light years, would take approximately 100,000 light years divided by the time it takes light to travel 1 light year at 17 kilometers per second instead of 300,000 kilometers per second. The ratio of those speeds is roughly 18,000 to 1. So the crossing time for Voyager 1 would be approximately 100,000 times 18,000 years, which is 1.8 billion years. Voyager 1, the fastest thing humans have ever built, would need 1.8 billion years to cross the Milky Way. It has been traveling for 47 years and has covered about 0.002 light years, less than 1/500th of 1% of the galaxy's width. Now let us talk about what is inside that disk. But before we do, let us anchor the size calculation with a physical comparison that makes it visceral. The diameter of the Earth is approximately 12,700 kilometers. The diameter of the Sun is approximately 1,400,000 kilometers. The Sun is about 109 times wider than the Earth. The distance from the Earth to the Sun is approximately 150 million kilometers. The Sun's own diameter is about 1/100th of the Earth-Sun distance, so the Sun at Earth's distance subtends an angle of about half a degree in the sky, which is why it looks like a disk and not a point. Now scale up to the Milky Way. The distance from the Earth to the Sun is 1 astronomical unit, 150 million kilometers. 1 light year is approximately 63,000 astronomical units. The diameter of the Milky Way is 100,000 light years, which is 100,000 times 63,000 astronomical units, or about 6.3 billion astronomical units. The ratio of the Milky Way's diameter to the Earth-Sun distance is about 6.3 billion. To put it another way, if the Earth-Sun distance were 1 millimeter, a small dot on a page, the Milky Way would be about 6,300 kilometers across. That is the distance from London to Los Angeles. 1 millimeter representing the Earth-Sun distance, and the galaxy is a continent wide. At this scale, the nearest star to the Sun, Proxima Centauri, 4.2 light years away, would be about 265 millimeters from your dot, about 26 centimeters, the width of a hardcover book. The Sun is a dot, the nearest star is a book width away, and the galaxy is a continent wide. Now let us talk about what is inside that disk. The most obvious contents are the stars, 300 billion of them in round numbers, but they are not distributed evenly. The center of the galaxy, the galactic bulge, contains a dense concentration of old stars packed into a roughly spheroidal region about 10,000 light years across. These are old stars, mostly, formed in the first few billion years of the galaxy's history, when gas was plentiful and star formation was intense. They are red and orange and yellow, cool, slow-burning, ancient. The bulge contains perhaps a quarter of all the galaxy's stars in a region that represents only a tiny fraction of the total volume. Beyond the bulge, the disk spreads outward in spiral arms. The Milky Way has two main spiral arms, the Scutum Centaurus arm and the Perseus arm, and two secondary arms, including the Orion Cygnus arm, which is a minor spur. The Sun lives in the Orion Cygnus arm, roughly 26,000 light years from the galactic center. Why spiral arms? That is a question that took most of the 20th century to answer, and the answer is stranger than intuition suggests. Spiral arms are not rigid structures. They are not like the blades of a pinwheel rotating together. If they were, they would wind up over time, the inner parts rotating faster than the outer parts, the arms wrapping tighter and tighter until they disappeared into the disk. This would happen in a few 100 million years. The galaxy is 13 billion years old. The arms would have been erased 25 times over. Instead, spiral arms are density waves. They are more like a traffic jam on a circular highway than like the spokes of a wheel. Cars moving along the highway slow down where the traffic is thick and speed up where it thins. Individual cars pass through the jam, enter the thick traffic, slow, then exit and speed up again. The jam itself moves much slower than the individual cars. The spiral arms of the Milky Way are density waves in the disk, regions where the interstellar gas and stars are temporarily more compressed. Individual stars pass through the arms over hundreds of millions of years, spending time in the denser region and then moving on. The reason this matters is that the compressed regions of the spiral arms are where stars form. When interstellar gas, mostly hydrogen, some helium, traces of heavier elements, is compressed by the density wave, it begins to collapse under its own gravity. Dense knots form within the collapsing gas. The knots grow denser, their cores heat up. When the core temperature reaches about 10 million degrees Celsius, hydrogen nuclei begin fusing into helium, releasing energy. A star ignites. So the spiral arms glow blue-white because they are full of freshly born, hot, massive stars. But the mechanism of star formation in those arms is worth explaining in detail because it is one of the more beautiful sequences in astrophysics. A typical molecular cloud in the Milky Way contains between 110 million solar masses of gas and dust, mostly hydrogen in molecular form, with traces of carbon monoxide, water, ammonia, formaldehyde, and more complex organic molecules. The cloud is cold, typically between 10 and 30 degrees above absolute zero. It is also dark. The dense gas and dust absorb and scatter visible light, which is why molecular clouds appear as dark patches against the background star field in photographs of the Milky Way. Despite being cold and dark, these clouds are in a state of constant competition between two forces. Gravity pulls the gas inward, trying to collapse the cloud. Thermal pressure pushes outward, resisting the collapse. For most of a molecular cloud's life, tens of millions of years, these forces are roughly balanced, and the cloud drifts through the galaxy in a kind of slow equilibrium. The balance breaks when something perturbs the cloud. The density wave of the spiral arm compresses it, increasing its density. A nearby supernova sends a shock wave through it, compressing certain regions above the threshold for gravitational instability. In those compressed regions, gravity begins to win. Dense knots form. Each knot contracts further, fragmenting into smaller and smaller clumps, each clump becoming denser and hotter as gravitational potential energy converts to thermal energy. The central region of each collapsing clump becomes a protostar, a hot, dense object not yet massive or hot enough at its core to sustain nuclear fusion. The protostar is surrounded by an accretion disk of infalling gas and dust, spiraling inward along the rotation axis. Material accretes from the disk onto the protostar. The protostar grows. Its core temperature rises. When the core temperature reaches about 10 million degrees Celsius, 10 million Kelvin. Hydrogen nuclei are moving fast enough to overcome their electrical repulsion and fuse. Four hydrogen nuclei combine to form one helium nucleus, releasing energy according to Einstein's equation relating mass and energy. The energy output stabilizes the protostar against further gravitational collapse. The star has reached the main sequence. It will stay there, fusing hydrogen to helium in its core, for billions of years if it is sun-like, or for millions of years if it is massive. The least massive stars that can sustain hydrogen fusion have about 8% of the sun's mass. Below that threshold, the core never reaches 10 million degrees, and the object becomes a brown dwarf, too big to be a planet, too small to be a star, slowly cooling and never igniting. Brown dwarfs may be as common as ordinary stars in the galaxy, though their low luminosity makes them difficult to detect. The most massive stars that form are perhaps 100 to 300 times the mass of the Sun. These objects are extremely rare, blazingly luminous, hundreds of thousands of times more luminous than the Sun, and extraordinarily short-lived. A star of 100 solar masses burns its hydrogen fuel in perhaps a few million years. Its entire lifespan is shorter than the time since the mass extinction that killed the non-avian dinosaurs 66 million years ago. When these massive stars die, they do not go quietly. They explode as core collapse supernovae, releasing more energy in 10 seconds than the sun will emit in its entire 10 billion year main sequence lifetime. The explosion is so energetic that it can briefly outshine the entire galaxy that contains it. The shockwave propagates outward through the surrounding interstellar medium at thousands of kilometers per second, compressing gas, heating it, potentially triggering the next generation of star formation in neighboring molecular clouds. The spiral arms are therefore not just regions of current star formation. They are engines of stellar ecology, where the deaths of massive stars drive the formation of the next generation, and the enrichment of the interstellar medium with heavy elements enables more complex chemistry in each successive cycle. Massive stars are blue. They burn intensely, using their hydrogen fuel rapidly, and they die within a few tens of millions of years. In astronomical terms, they are mayflies. When you see the blue shimmer of a spiral arm in an image of a distant galaxy, you are seeing the light of stars that were born in that arm recently and will be dead before the arm has moved far. The Sun was not born in the Orion Cygnus arm where it currently lives. It has orbited the galaxy roughly 20 times in its 4.5 billion year lifetime, passing through different arm regions, spending time in the interarm regions, arriving at its current position within the Orion Spur through the slow accumulation of orbits. The Sun will not stay here. It is moving as everything in the galaxy moves, in a roughly circular orbit around the galactic center at roughly 220 kilometers per second. At 220 kilometers per second, the Sun takes approximately 225 million years to complete one orbit of the galaxy. Let us calculate that precisely. The Sun orbits at approximately 26,000 light years from the galactic center. The circumference of a circle with this radius is 2 times pi times 26,000 light years. 2 times pi is approximately 6.28. 6.28 times 26,000 is approximately 163,000 light years. That is the distance the Sun travels in one galactic orbit. 1 light year is the distance light travels in 1 year, about 9.5 trillion kilometers. So 163,000 light years is 163,000 times 9.5 trillion kilometers, which is about 1.5 times 10 to the 18th power kilometers. The Sun moves at 220 kilometers per second. There are approximately 3.1 times 10 to the 7th power seconds in 1 year. So the sun covers 220 times 3.1 times 10 to the seventh power kilometers per year, which is about 6.8 times 10 to the ninth power kilometers per year. Divide the circumference by the annual distance. 1.5 times 10 to the 18th power divided by 6.8 times 10 to the ninth power gives approximately 2.2 times 10 to the eighth power years. That is about 220 million years per orbit. 220 million years. The last time the Sun was at its current position in its galactic orbit, the Triassic period was just beginning on Earth. Dinosaurs had not yet evolved. The age of mammals, let alone the age of humans, lay more than 200 million years in the future. The Sun has completed this orbit approximately 20 times since its formation. Each time around, the solar system has passed through different regions of the galaxy, different spiral arms, different stretches of interarm space, different local environments with different densities of interstellar gas and different rates of nearby supernova explosions. The galactic environment of the solar system has varied significantly over its history. At 220 kilometers per second, the Sun takes approximately 225 million years to complete one orbit of the galaxy. Astronomers call this the galactic year or the cosmic year. The Sun has completed approximately 20 galactic years since its formation. The last time the Sun was at its current position in its orbit, the dominant life on Earth was early dinosaurs. The time before that, the Permian extinction was just ending. Let us now talk about what is at the center of all of this orbiting, because the galactic center is not simply a dense concentration of old stars. There is something else there. Something that took most of the 20th century to find and whose nature still pushes the boundaries of physics. Before we go to the center, let us acknowledge what it took to know where the center is. For most of human history, the structure of the Milky Way was entirely unknown. Ancient peoples could see the band of light crossing the sky, but they had no way to know that it was a disk of stars seen edge on, or that the sun was one of hundreds of billions of stars inside it, or that the galaxy had a center at all. The first systematic attempt to measure the structure of the Milky Way was made by William Herschel in the late 18th century. Herschel and his sister Caroline counted stars in different directions across the sky, assuming that where more stars were visible, the galaxy extended farther. The resulting grindstone model placed the sun near the center of a flattened disk. This was wrong. Herschel could not know that dust in the interstellar medium blocked his view of the more distant parts of the galaxy. But it established the method of using stellar counts to probe the galactic structure. In the early 20th century, Harlow Shapley made a crucial observation. He measured the distances to about 100 globular clusters, the ancient spherical collections of hundreds of thousands of stars that orbit the Milky Way, using Cepheid variable stars as distance indicators. The globular clusters were distributed in a roughly spherical arrangement, but the center of that arrangement was not the sun. The center was about 30,000 light years away in the direction of Sagittarius. Shapley recognized that the globular clusters orbit the center of the galaxy, and their distribution revealed where that center was. Shapley was right that the sun is not at the galactic center. He overestimated the distance to the center. He got about 50,000 light years, and we now know it is about 26,000. But the fundamental insight was correct. The Earth is not at the center of the universe, or even at the center of our own galaxy. We are in the outskirts, 2/3 of the way from the center to the visible edge. This was a profound displacement. It was the last in a long series of decenterings. Copernicus moved Earth from the center of the solar system. Herschel and Shapley moved the sun from the center of the galaxy. Hubble showed that the galaxy itself was one of billions. And dark energy is showing us that even the observable universe is not the full extent of what exists. At the precise center of the Milky Way, hidden behind roughly 26,000 light years of intervening gas and dust that blocks all visible light, sits a supermassive black hole. It is called Sagittarius A star, named for the radio source first detected in that direction in 1974. Its mass is approximately 4 million times the mass of the Sun. 4 million solar masses compacted into a region smaller than our solar system. To put that mass in perspective, let us do the calculation. The Sun has a mass of approximately 2 times 10 to the 30th power kilograms. 4 million solar masses is therefore 4 million times 2 times 10 to the 30th power kilograms, which is 8 times 10 to the 36th power kilograms. The Schwarzschild radius of a black hole, the radius of the event horizon, the point of no return, is equal to 2 times the gravitational constant times the mass, divided by the square of the speed of light. Plugging in these numbers, the event horizon of Sagittarius A star has a radius of approximately 12 million kilometers. 12 million kilometers sounds large. The Sun has a radius of approximately 700,000 kilometers, so the event horizon of the black hole at the center of our galaxy is about 17 times the radius of the Sun. The entire solar system, from the Sun to the orbit of Pluto, spans roughly 6 billion kilometers in radius. 12 million kilometers is only a small fraction of that. The most massive object in the galaxy, 4 million solar masses, occupies a region smaller than the distance from the Sun to Venus. The Schwarzschild radius calculation is worth doing precisely because it reveals something counterintuitive. A black hole of 4 million solar masses is not an extraordinarily dense object in the conventional sense. The average density of the region enclosed by the event horizon is mass divided by volume. 4 million solar masses divided by a sphere of radius 12 million kilometers. Calculate the volume. 4/3 times pi times 12 million cubed kilometers, which is about 7.2 times 10 to the 21st power cubic kilometers. The density is 4 million solar masses, about 8 times 10 to the 36th power kilograms, divided by about 7.2 times 10 to the 21st power cubic kilometers, converted to cubic meters by multiplying by 10 to the 9th power. The average density within the event horizon of Sagittarius A star is roughly 1,000 kilograms per cubic meter, about the density of water, dense by ordinary standards. But not extraordinarily so. The extraordinary feature of a black hole is not its density, but its geometry. Space-time itself is curved so severely that no path leads outward. How do we know it is there? We cannot see it directly. Visible light from the galactic center is blocked by about 30 magnitudes of extinction from intervening dust, meaning the light is dimmed by a factor of roughly a trillion. But infrared and radio waves can penetrate that dust. Starting in the 1990s, two independent teams began working on what would become one of the most technically demanding projects in modern astronomy, directly observing the gravitational influence of the central black hole by tracking the individual orbits of stars within a few light years of the galactic center. The challenge was formidable. The galactic center is 30,000 light years away. Even the sharpest ground-based optical telescopes, limited by the blurring effect of Earth's turbulent atmosphere, could not resolve individual stars at that distance. And visible light cannot penetrate the intervening dust anyway. The observations had to be done in the near-infrared, wavelengths just longer than visible red light, where the dust is more transparent. Adaptive optics was the breakthrough technology. By measuring atmospheric turbulence in real time using a bright reference star near the target field and continuously deforming a small mirror to counteract the turbulence at kilohertz frequencies, adaptive optics can recover something close to the theoretical diffraction limit of a large telescope. On an 8-meter telescope, about the diameter of the primary mirrors at the Keck Observatory on Mauna Kea and at the Very Large Telescope in Chile, the two sites used by the two competing teams, this means achieving angular resolutions of about 50 milliarcseconds in the near-infrared. At the distance of the galactic center, 50 milliarcseconds corresponds to about 2,000 astronomical units, about two-thirds of a light year, good enough to separate individual stars if they are not too densely packed. Each team took image after image of the galactic center over years, tracking the precise positions of individual stars. The positions shifted, stars moved, and the motions were not random. They followed elliptical paths around a common focus. Kepler's laws applied. The orbital periods ranged from about 16 years for the tightest known orbit to thousands of years for stars on wider paths. From the orbital parameters of dozens of stars, both teams independently calculated the mass of the central object, approximately 4 million solar masses, concentrated in a region at most a few light hours across. No known collection of ordinary objects, stars, neutron stars, stellar mass black holes, could be that massive and that compact without themselves collapsing into a black hole. The only consistent explanation was a single supermassive black hole. Starting in the 1990s, two independent teams, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, and one led by Andrea Ghez at the University of California, Los Angeles, began tracking the orbits of individual stars near the galactic center using adaptive optics on large infrared telescopes. Adaptive optics is a technique that corrects for atmospheric turbulence in real time by measuring the distortion of a reference star and using a deformable mirror to counteract it. What they found was extraordinary. Stars near the galactic center orbit at enormous velocities on very tight trajectories. One star, designated S2, orbits the galactic center with a period of approximately 16 years and reaches speeds of nearly 28 million kilometers per hour at its closest approach. Another star, S4714, passes within less than 100 astronomical units of the central mass. From the orbital parameters, the period, the semi-major axis, the eccentricity, you can calculate the mass of the central object using Kepler's third law. The mass required to produce those orbits is precisely 4 million solar masses, concentrated in a region far too small to be any known collection of ordinary stars or gas. The conclusion is unavoidable. There is a supermassive black hole at the center of the Milky Way. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this discovery, 3 years before the Event Horizon Telescope produced the first image of Sagittarius A star itself, a glowing ring of superheated gas surrounding a dark central shadow, exactly as general relativity predicts. Now let us step back from the center and think about the structure of the disk more carefully, because there is something about the disk that turns out to be even more significant than the spiral arms or the central black hole. The disk of the Milky Way, the region containing the spiral arms and most of the stars, is embedded inside something far larger that cannot be seen at all. In the 1970s, astronomer Vera Rubin and her instrument specialist Kent Ford conducted a systematic survey of the rotation velocities of stars in the outer Milky Way. They were following up on earlier, less precise measurements that had already suggested something was wrong. Here is what should happen. In the solar system, as Johannes Kepler established in the early 17th century and Isaac Newton explained theoretically 60 years later, the orbital speed of any body around a central mass decreases predictably with distance. The mathematical relationship is precise. Orbital velocity is proportional to the square root of the mass divided by the radius. Double the orbital radius, and the orbital speed drops by roughly 30%. Quadruple the radius, and the speed halves. This prediction works with extraordinary precision everywhere we can test it. The planets orbit exactly as Kepler and Newton predicted. Artificial satellites orbit exactly as predicted. Binary star systems orbit exactly as predicted. The agreement between theory and observation is so good that when a 19th century astronomer named Urbain Le Verrier noticed that Mercury's orbit precessed slightly faster than Newton's theory predicted, it was taken as evidence that something was wrong with Newton's theory, and the anomaly was eventually explained by Einstein's general theory of relativity in 1915. This context matters for appreciating what Vera Rubin found. She was not working in a domain where theory was uncertain. She was testing well-established physics in a new regime, the outer regions of spiral galaxies, expecting to confirm what everyone assumed was already known. In the solar system, planets far from the sun orbit slowly because the gravitational influence of the sun weakens with distance. Jupiter orbits at 13 kilometers per second, Neptune at 5 kilometers per second. The pattern follows precisely from Newton's law of gravity, and it follows because almost all of the solar system's mass is concentrated at the center, in the sun. The same logic should apply to the Milky Way. Most of the galaxy's visible mass, the stars and gas, is concentrated in the central bulge and inner disk. Stars in the outer disk should feel a weaker gravitational pull and should therefore orbit more slowly, predictably, measurably more slowly. The expected curve of orbital velocity versus distance from the galactic center should slope downward at large radii. What Rubin and Ford found was that it did not. Stars in the outer Milky Way and in every other spiral galaxy they subsequently measured, dozens and then hundreds, orbited at roughly the same speed as stars in the inner disk. The velocity curve was flat, not declining, flat. A flat rotation curve has one physical interpretation. The mass enclosed within any given radius keeps growing proportionally with that radius, even where there are no visible stars or gas. There is mass out there. It is everywhere. It surrounds the galaxy like an enormous invisible sphere extending far beyond the visible disk, perhaps 2 to 3 times the diameter of the disk in all directions. This unseen component contributes perhaps 5 to 6 times more mass to the Milky Way than all the visible stars and gas combined. We call it dark matter, and we do not know what it is. Let us be precise about what that means. It is not that we have named an unknown and pretended to understand it. We have extremely precise measurements of dark matter's gravitational effects. The rotation curves, the velocity dispersions of galaxies in clusters, the gravitational lensing of background galaxies, by foreground mass distributions, the acoustic oscillations in the cosmic microwave background that encode the ratio of dark matter to ordinary matter in the early universe. All of these measurements are consistent and complementary. The dark matter halo of the Milky Way, the dark matter in clusters, and the dark matter in the early universe are described by the same model with the same parameters. This consistency across vastly different scales and vastly different observational techniques gives us confidence that dark matter is real. The direct detection experiments are sophisticated operations. The Panda X detector in China, the Lux Zeppelin detector in a former gold mine in South Dakota, the N1T and XN detectors in the Gran Sasso Underground Laboratory in Italy. These instruments contain hundreds of kilograms to multiple tons of liquid xenon, purified to extraordinary levels of radio purity, buried under kilometers of rock to shield them from cosmic rays. The principle is that a dark matter particle passing through the detector might occasionally collide with a xenon nucleus and produce a tiny flash of light and a small electrical signal. The experiments are sensitive enough to detect collisions with energies, equivalent to a few atomic nuclei vibrating. They have run for years without detecting anything above background. This non-detection is not failure, it is science. Each year without detection rules out a larger portion of the possible parameter space for WIMP dark matter. The experiments have now eliminated most of the parameter space where WIMPs were predicted to live based on simple supersymmetric models. This puts pressure on theorists to develop new models that predict dark matter candidates outside the excluded ranges. The axion search is at an earlier stage but accelerating. Axions were proposed in 1977 by Roberto Peccei and Helen Quinn to solve a specific problem in quantum chromodynamics, the strong force, and it was recognized by Frank Wilczek and Steven Weinberg independently that the proposed Peck-Quinn mechanism would produce a new particle, which Wilczek named the axion. Light axions, if they exist, could make up the dark matter. Detecting them requires different techniques than WIMP detectors, typically resonant microwave cavities in strong magnetic fields, tuned to detect the conversion of axons to photons. The AtomX experiment at the University of Washington is the leading axon search, and it has begun to probe the parameter space where axons are expected to live. We have extremely precise measurements of dark matter's gravitational effects and extremely detailed models of its spatial distribution. The dark matter halo of the Milky Way is roughly spherical, with a density that peaks at the center and falls off predictably with radius according to a profile first described by Julio Navarro, Carlos Frank, and Simon White in the 1990s, the NFW profile. The total mass of the Milky Way's dark matter halo is estimated at roughly 1 trillion solar masses, about 10 times the mass of all the visible stars and gas. But what dark matter is made of, what particles constitute it, is unknown. The leading hypothesis for decades was that it consists of weakly interacting massive particles, or WIMPs, hypothetical particles that interact through gravity and the weak nuclear force, but not through electromagnetism, which is why they neither emit nor absorb light. Enormous underground detectors filled with liquid xenon have searched for WIMPs for more than 2 decades. No detection. Other candidates include axions, extremely light particles originally proposed to solve an unrelated problem in quantum chromodynamics, and primordial black holes formed in the early universe. None confirmed. One alternative framework, called modified Newtonian dynamics, or MOND, proposed by physicist Mordechai Milgram in 1983, tries to explain the flat rotation curves without invoking dark matter at all. MOND modifies Newton's second law, force equals mass times acceleration, in the regime where accelerations are very small, below a characteristic acceleration of about 1.2 times 10 to the minus 10 meters per second squared. Below this threshold, the relationship between force and acceleration changes from linear to different behavior in a way that produces flat rotation curves naturally. MOND is a serious scientific proposal. It makes specific, testable predictions for the rotation curves of galaxies, and it succeeds remarkably well for many isolated spiral galaxies, especially low surface brightness dwarf galaxies, where its predictions are more accurate than standard dark matter models without careful tuning. This success is real, not coincidental, and it has motivated ongoing theoretical work trying to embed MOND-like behavior into a relativistic theory. But MOND has serious problems. It fails at the scale of galaxy clusters, the same scale where Zwicky's original calculation showed the missing mass problem in 1933. Galaxy clusters have more missing mass than MOND can account for. More importantly, the bullet cluster, a system of two galaxy clusters that collided and passed through each other, observed in X rays and gravitational lensing, provides what many scientists consider the most direct evidence for dark matter as a real physical substance. In the bullet cluster, the hot gas from both clusters was slowed by electromagnetic interactions during the collision, while the dark matter halos passed through each other without slowing. The gravitational lensing map of the system, showing where the mass is, does not coincide with the X-ray map, showing where the gas is. The mass is where the galaxies are, not where the gas is. This is exactly what dark matter models predict, and exactly what Mond cannot easily explain without adding extra mass anyway. One alternative framework, called modified Newtonian dynamics or MOND, proposed by physicist Mordechai Milgram in 1983, tries to explain the flat rotation curves without invoking dark matter at all, instead modifying the law of gravity at very low accelerations. MOND works well for isolated galaxies, especially low surface brightness dwarf galaxies, where its predictions are remarkably accurate. But MOND fails at the scale of galaxy clusters, and it cannot reproduce the pattern of acoustic peaks in the cosmic microwave background. Dark matter models can. The scientific consensus remains firmly with dark matter. What we can say is this: the Milky Way you see in the night sky is the luminous, visible fraction of a much larger structure. The spiral disk, the bulge, the 400 billion stars, they are the glowing ember at the heart of a dark matter halo that extends 300,000 light years in all directions. What you see is the tip of the structure. The halo is the structure. Now, let us talk about where we actually are in this structure, because the sun's position in the Milky Way turns out to be neither random nor particularly central, and understanding it requires thinking about what the galaxy looked like when our star formed. The sun formed approximately 4.6 billion years ago from a collapsing molecular cloud in what is now the Orion Cygnus arm of the Milky Way. The molecular cloud was not primordial. It was not left over from the Big Bang. It was enriched by several generations of preceding stars whose supernova deaths scattered heavy elements, carbon, oxygen, silicon, iron, into the interstellar medium before the cloud that became our solar system collapsed. The enrichment tells us something important about timing, and to appreciate what it tells us, we need to understand the galactic chemical history in some detail. The universe that emerged from the Big Bang approximately 13.8 billion years ago contained hydrogen, helium, and trace amounts of lithium and beryllium. That was it. No carbon, no oxygen, no silicon, no iron, no calcium, no phosphorus, no sulfur, nothing capable of building rocky planets or biological chemistry. The periodic table as we know it did not yet exist in any useful sense. The elements heavier than helium, every element from carbon through uranium, were made inside stars and distributed by stellar death. This is one of the most profound facts in astronomy, and it has a precise timeline. The first stars formed within a few 100 million years of the Big Bang. These population 3 stars formed from gas that was 93% hydrogen and 7% helium with trace lithium. Having no heavy elements means having no efficient radiative cooling mechanism. Ordinary interstellar clouds cool efficiently because carbon and oxygen can emit photons at specific infrared wavelengths, carrying away thermal energy and allowing the gas to cool and contract. Without these coolants, the primordial gas clouds stayed hotter for longer during collapse, and the fragments that formed were larger. Population 3 stars are predicted by theory to have been massive, perhaps tens to hundreds of times the mass of the sun, and possibly some were even more extreme, approaching 1,000 solar masses. We have not directly observed a population 3 star. None exist anymore. They all died long ago, burning through their fuel in a few million years. but we see their chemical fingerprints in the oldest surviving stars, which show the enrichment pattern expected from population 3 supernova nucleosynthesis. After the first population 3 supernovae, the interstellar medium contained the first heavy elements: carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, and iron from the cores of massive stars. The second generation of stars, population 2, formed from this enriched gas. They were less massive on average, longer lived. Many population 2 stars survive today, 12 billion years old, their ancient chemical composition preserved like a record of the early galaxy. These old stars are found primarily in the galactic halo and in globular clusters, dense spherical collections of hundreds of thousands of stars that orbit the Milky Way like satellites and were among the first structures to form. Globular clusters are extraordinary objects. The Milky Way contains about 150 known globular clusters. The most luminous, Omega Centauri, contains approximately 10 million stars in a sphere about 150 light years across. The average distance between stars at its center is roughly 1/10 of a light year, about 1,000 times denser than the stellar neighborhood around the Sun. Omega Centauri may actually be the stripped remnant of a small galaxy that merged with the Milky Way billions of years ago. Its outer stars, stripped by tidal forces, and its core surviving as what we call a globular cluster. Over several billion years, multiple generations of stars enriched the interstellar medium progressively. Each round of star formation, stellar evolution, and supernova produced more heavy elements. The fraction of heavy elements in the interstellar medium, astronomers call this the metallicity, using metal to mean any element heavier than helium, grew from essentially zero in the first galaxies to the current value of about 1 to 2% by mass in the Sun's formation region. That 1 to 2% made all the difference. The universe is approximately 13.8 billion years old. The Milky Way began forming within the first billion years from dense regions of dark matter and primordial hydrogen and helium that collapsed under gravity. The first generation of stars in the galaxy, the so-called population 3 stars, were massive, hot, short-lived, and made entirely of hydrogen and helium. They had no heavy elements because the universe had not yet made any. They died as supernovae within a few million years, seeding the interstellar medium with carbon, oxygen, neon, silicon, sulfur, the first metals. The second generation of stars, population 2 stars, formed from that metal-enriched gas. They were less massive on average, longer lived. Many population 2 stars are still burning today, 12 billion years later. They are the old stars of the galactic halo and bulge, and their chemical composition, with very low heavy element abundances, is a fossil record of the early universe. The Sun belongs to a third generation. Population 1 stars, formed from gas enriched by multiple rounds of stellar evolution and supernova nucleosynthesis over several billion years. The Sun contains roughly 1.3% heavy elements by mass, about 20 times more than a typical old population 2 star. That enrichment is why there are rocky planets in the solar system. There was enough silicon and iron and magnesium in the collapsing cloud to build solid worlds. In the earliest galaxies, with their metal-poor gas, rocky planets may have been rare. We are the product of 10 billion years of galactic chemistry. The carbon in your body was made in the helium-burning shells of red giant stars. The oxygen was made in the same shells and in supernova explosions. The calcium in your bones was made in supernovae. The iron in your blood was made in the cores of massive stars that died in catastrophic collapses, releasing more energy in 10 seconds than the sun emits in its entire 10 billion year lifetime, scattering their iron to the cosmos. You are the third generation. Your atoms have been through stars. Now, let us talk about the neighborhood immediately surrounding the sun because it is smaller and stranger than most people realize, and it connects directly to one of the most consequential facts about the solar system's history. The sun sits inside a region called the local bubble, an irregular, roughly spherical cavity in the interstellar medium approximately 1,000 light years across, within which the density of gas is about 100 times lower than the galactic average. The local bubble was carved by a series of supernova explosions over the past 15 million years. Massive stars in what is now the Scorpio-Centaurus Association died in supernovae, each one driving a shock wave outward through the interstellar medium, blowing away gas and dust, creating a growing cavity. The hot, thin gas that fills the local bubble today is the remnant plasma from those ancient explosions. The sun moved into this cavity roughly 5 million years ago, roughly the time of the split between the human lineage and the chimpanzee lineage. Whether the low density environment of the local bubble had any influence on Earth's climate or evolutionary history is speculative, but the timing is at minimum interesting. Within the local bubble, the interstellar medium is about 100 times less dense than the galactic average. But even within this rarefied environment, the sun creates its own microenvironment, the heliosphere. The heliosphere is the region of space dominated by the solar wind, a continuous stream of charged particles, mostly protons and electrons, blowing outward from the sun's corona at speeds of roughly 400 to 800 kilometers per second. The solar wind carries the sun's magnetic field outward into space, stretching it into a spiral pattern as the sun rotates. This spiral, the Parker spiral, named for astrophysicist Eugene Parker, who predicted its structure in 1958, reaches throughout the heliosphere. The outer boundary of the heliosphere is called the heliopause, the surface where the solar wind pressure equals the pressure of the surrounding interstellar medium. Beyond the heliopause, the interstellar medium dominates. Inside the heliopause, solar wind dominates. The Voyager 1 spacecraft, the first human-made object to cross the heliopause, did so in 2012, approximately 35 years after its launch, at a distance of about 120 astronomical units from the Sun, about 18 billion kilometers. Between the heliopause and the region where the solar wind is still supersonic, there is a transition region called the heliosheath, bounded on the sun side by the termination shock, the surface where the solar wind abruptly slows from supersonic to subsonic speeds as it encounters the back pressure of the interstellar medium. Voyager 1 crossed the termination shock in 2004 at a distance of about 94 astronomical units. The heliosphere is not a sphere. It is shaped by the sun's motion through the interstellar medium. The solar wind carves a blunt-nosed shape in the direction of the sun's motion through the local interstellar medium, with a long tail trailing behind. The heliosphere is roughly football-shaped, elongated in the direction of motion. The significance of the heliosphere for life on Earth is often underappreciated. Cosmic rays, high-energy protons, and other particles accelerated by supernovae and other energetic events in the galaxy fill interstellar space at significant intensity. Many of these particles are deflected or decelerated by the heliosphere before they can reach Earth. The heliosphere is not an impenetrable barrier. Many stars do reach Earth to Earth, and they are a significant source of natural radiation, but it substantially reduces the cosmic ray flux inside the solar systems compared to interstellar space. Without the heliosphere, the cosmic ray dose at Earth's surface would be significantly higher, potentially influencing evolutionary processes over long timescales. Within the local bubble, the interstellar medium is about 100 times less dense than the galactic average, roughly 1/100th of an atom per cubic centimeter, rather than the typical 1 atom per cubic centimeter. The reduced density means reduced shielding from cosmic rays in some respects, though the solar, wind, and Earth's own magnetic field provide the primary protection from energetic particles at the scale of the solar system. The boundaries of the local bubble are visible in maps of interstellar dust and neutral hydrogen. The bubble is defined by a wall of denser neutral gas and dust that surrounds it. The Scorpius-Centaurus OB Association, the group of young, massive stars whose supernovae carve the bubble, is visible in the southern sky as a loose association of bright blue-white stars. These stars are the second and third generation of star formation triggered in the region. The first generation died in the supernovae that created the bubble, and the survivors are their younger siblings, still hot and bright and destined to die in their own supernovae within the next few million years. Adjacent to the local bubble, at varying distances, are other bubbles and cavities carved by other supernova sequences. The Loop I superbubble, centered on the Scorpius-Centaurus Association, connects to the local bubble along one wall. The interstellar medium of the Milky Way is not a smooth, uniform medium. It is a complex, turbulent, three-dimensional foam of hot, thin bubbles, warm, neutral clouds, cold, dense molecular clouds, and the interfaces between them. Star formation and stellar death are constantly reshaping this foam on timescales ranging from millions to hundreds of millions of years. Within this complex medium, the sun plows along at roughly 20 kilometers per second relative to the local standard of rest, the average motion of nearby stars. This velocity means the heliosphere, the bubble of solar wind that surrounds the solar systems, carves through the interstellar medium like a boat through water, compressed on the leading edge and elongated on the trailing edge. The interstellar medium flows around and past the heliosphere continuously. The sun moved into this cavity roughly 5 million years ago, roughly the time of the split between the human lineage and the chimpanzee lineage. Whether the low-density environment of the local bubble had any influence on Earth's climate or evolutionary history is speculative, but the timing is at minimum interesting. Within the local bubble, the sun's nearest stellar neighbors are well measured. The closest star system is Alpha Centauri, a triple system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are similar to the Sun, main sequence stars with masses of 1.1 and 0.9 solar masses, respectively, bound in a binary orbit with a period of roughly 80 years and a separation that varies between 11 and 36 astronomical units. Proxima Centauri is a red dwarf star about an eighth of the Sun's mass, orbiting the AB pair at a distance of about 15,000 astronomical units, roughly a quarter of a light year, with an orbital period of approximately 550,000 years. The total distance from the Sun to the Alpha Centauri system is approximately 4.2 light years. In the grain of sand scale, where the Sun is shrunk to 1 millimeter, 1 light year is approximately 6,000 kilometers. 4.2 light years is about 25,000 kilometers. So in a model where the Sun is a grain of sand, the nearest stellar neighbor is another grain of sand sitting 25,000 kilometers away. The circumference of the Earth is about 40,000 kilometers. The nearest star, at grain of sand scale, is about 60% of the way around the Earth. This is the density of the stellar neighborhood, not crowded, not packed. Isolated points of fire separated by distances so vast that traveling between them at any speed currently achievable by human technology would take tens of thousands of years. Proxima Centauri has attracted particular attention because it hosts at least 2 confirmed planets and possibly a third. Proxima b was confirmed in 2016, A planet with a minimum mass of about 1.1 Earth masses, orbiting in the habitable zone at a distance of about 0.05 astronomical units, completing one orbit every 11.2 days. That 11-day orbital period immediately reveals a problem. Proxima Centauri is a red dwarf, and red dwarfs are much dimmer and cooler than the Sun. The habitable zone, where liquid water could exist on a planetary surface, is therefore much closer to the star than in the solar system. Mercury orbits the Sun at about zero point 0.4 astronomical units. Proxima b orbits Proxima Centauri at 0.05 astronomical units, 8 times closer than Mercury is to the Sun. At such a close distance, a planet faces a phenomenon called tidal locking. The same tidal forces that are gradually slowing Earth's rotation and making the moon always show the same face to Earth would, on a timescale of perhaps a few billion years, lock Proxima b so that one side faces the star permanently and the other side faces permanent night. If tidally locked, Proxima b would have a permanent day side blasted by stellar radiation and a permanent night side that could be cold enough to freeze any atmosphere. Whether tidal locking has occurred for Proxima b is uncertain. The planet's orbital history and the star's history both matter. But even if the planet is tidally locked, atmospheric circulation could potentially redistribute heat from the day side to the night side. Computer models of tidally locked planets suggest they might maintain habitable surface temperatures in certain configurations. The deeper problem is Proxima Centauri's flare activity. Red dwarfs, despite being small and cool, are often extremely active magnetically. Proxima Centauri produces large stellar flares regularly, intense bursts of ultraviolet and X-ray radiation that at the distance of Proxima b are vastly more intense than the solar flares that occasionally disrupt Earth's communications and power grids. A major Proxima flare was detected in 2019 that was 14,000 times brighter in ultraviolet wavelengths than normal. Such flares could strip the atmosphere from any planet in the habitable zone unless the planet has a strong magnetic field, and whether Proxima b has a magnetic field is unknown. This tension, the tantalizing proximity and Earth-like mass on one hand, the hostile radiation environment on the other, makes Proxima b one of the most studied objects in exoplanet science. Its existence does not confirm that life is there. Its existence tells us that a rocky world in the habitable zone of the nearest star is possible, and that the universe does not waste habitable zone real estate. Proxima Centauri has attracted particular attention because it hosts at least two confirmed planets, including Proxima b, which orbits in the habitable zone, the range of distances from the star where liquid water could theoretically exist on a rocky surface. Proxima b receives roughly the same energy from Proxima as Earth receives from the Sun, but Proxima is a flare star. It emits intense ultraviolet and X-ray flares at a much higher rate than the Sun, potentially stripping the atmosphere of any planet in the habitable zone. Whether Proxima b has any atmosphere and whether it could retain one over geological time is currently unknown. It is the closest potentially habitable planet outside the solar system. We do not yet know if it is anything more than a rock. Beyond Alpha Centauri, the next nearest systems are Barnard's star at 5.9 light years, a red dwarf with a single known planet candidate, Wolf 359 at 7.8 light years, Lalande 21185 at 8.3 light years, and Sirius at 8.6 light years. Sirius is the brightest star in the night sky as seen from Earth, not because it is intrinsically extremely luminous, but because it is relatively nearby. Intrinsically, it is about 25 times more luminous than the Sun, a young, hot Whiteman sequence star with a white dwarf companion in a 50-year orbit. Within 10 light years of the Sun, there are approximately 12 known star systems. Let us extend that survey outward. Within 100 light years, the census grows to several thousand star systems. Within that sphere, the distribution of star types reflects the galaxy's overall stellar population. About 75% are red dwarfs, the most common type of star, dim and long lived. About 12% are orange K type stars, slightly more massive than red dwarfs, but still dimmer than the Sun. About 7% are yellow G type stars like the Sun. About 4% are slightly more massive and hotter yellow white F type stars. The remainder are rare massive blue white A type, B type, and O type stars, which are intrinsically far more luminous but also far less numerous. Stars are not uniformly distributed among these types by any measure proportional to their luminosity. The most luminous stars, the hot blue giants, are so rare that within 100 light years there may be only a handful. The most common stars, the red dwarfs, are so dim that most of them were unknown until modern survey programs with sensitive instruments began systematically cataloging them. The nearest known red dwarf to the Sun, which is to say, the nearest star that is not part of the Alpha Centauri system, is Barnard's star at 5.9 light years. It is the star with the highest proper motion across the sky, moving about 10.3 arcseconds per year relative to background stars, fast enough to be measurable over a human lifetime. Barnard's star has a single candidate planet detected by radial velocity measurements, though its existence has been disputed and is not confirmed to the same standard as the Proxima planets. The variety within just the nearby stellar census is instructive. Some of these nearby stars are younger than the Sun. They formed more recently from gas enriched by more recent generations of supernovae, and they are chemically slightly more metal rich. Some are older, with compositions preserving the lower metallicity of the interstellar medium from several billion years before the Sun formed. Some are binaries. Most are single. Most are intrinsically dimmer than the Sun, making the solar neighborhood an unusually well-illuminated part of the galaxy from Earth's surface perspective. The existence of planets around these nearby stars has transformed from speculation to established fact in the past 3 decades. Before 1995, no planet outside the solar system had been confirmed. Since the first exoplanet detection around a Sun-like star, 51 Pegasi b, detected by Michel Mayor and Didier Queloz, thousands have been confirmed, and statistical inference from the Kepler's Space Telescope's survey suggests that most stars in the Milky Way host at least one planet. The galaxy is not a sparse collection of isolated suns. It is a planet-rich environment in which worlds are the norm, not the exception. Whether any of those planets harbors life is unknown. The question of life elsewhere in the Milky Way is one of the most significant open questions in all of science, and we have no confirmed answer. But the question has changed character in the last 30 years. From are there planets to are there planets with the right conditions, and increasingly to are there signals we can detect. Within 10 light years of the Sun, there are approximately 12 known star systems containing about 17 individual stars. All but Sirius are dimmer than the Sun. Most are red dwarfs, which are by far the most common type of star in the galaxy. Red dwarfs have masses between 8% and 50% of the Sun's mass, burn their hydrogen so efficiently that they can live for trillions of years, and are so dim that none of them are visible to the naked eye from Earth, despite being our closest neighbors. This gives us an accurate picture of the stellar neighborhood, sparse, dominated by small, dim stars, with occasional bright exceptions like Sirius. The Sun is not typical in being a solitary star. About half of all stars are in binary or multiple systems, but the Sun is reasonably typical in terms of mass and luminosity. It is in the upper third of stellar masses in the galaxy, slightly brighter than average, a middle-aged G-type main sequence star that will continue burning hydrogen for roughly another 5 billion years. Those 5 billion years are not a blank. There is a schedule, and it is written in the physics of stellar evolution with considerable precision. The Sun is currently in what astronomers call the middle of its main sequence lifetime. It formed about 4.6 billion years ago from the gravitational collapse of a molecular cloud in the Orion Cygnus arm of the Milky Way. The cloud collapsed, fragmented, and formed a dense protostellar core surrounded by a rotating accretion disk. Over about 100 million years, the protostar gathered mass from the disk and from surrounding gas, contracted, heated its core, and eventually ignited hydrogen fusion. Since then, the Sun has been fusing approximately 600 million tons of hydrogen into helium every second. 600 million tons per second sounds like an enormous fuel consumption rate. The Sun's total mass is about 2 times 10 to the 30th power kilograms, 2 billion trillion kilograms. At the fusion rate, the Sun converts about 5.4 times 10 to the 21st power grams of hydrogen to helium per year, losing a tiny fraction of its mass to energy via Einstein's mass-energy equivalence. At this rate, the Sun would consume its entire mass in roughly 37 billion years. But the Sun does not fuse all its mass. Only the hydrogen in its core, where temperatures are high enough for fusion, is available as fuel. The core comprises roughly 10% of the Sun's mass. 10% of the Sun's mass at current consumption rates will last about 5 billion more years, but the Sun will not maintain exactly its current luminosity for those 5 billion years. As hydrogen fuses to helium in the core, the proportion of helium rises and the proportion of hydrogen falls. Helium nuclei are heavier and denser than hydrogen nuclei, so as the helium fraction rises, the core contracts slightly under the additional weight, heats up, and drives the nuclear reactions faster. The net effect is a gradual increase in luminosity over the Sun's main sequence lifetime. The Sun is currently about 30% more luminous than when it formed 4.6 billion years ago. In 5 billion years, it will be another 60% more luminous than today. The consequences for Earth are stark. The increased luminosity will raise surface temperatures. Earth's oceans will begin to evaporate progressively. Water vapor enters the upper atmosphere, where ultraviolet radiation splits it into hydrogen and oxygen, the hydrogen escaping to space and the oxygen remaining. This runaway water loss is effectively irreversible. Once started, it continues until the oceans are gone. The timeline for this process, depending on climate feedbacks and biological activity, is roughly 1 to 1.5 billion years from now. 1 billion years is a long time on human scales, 100 times the history of complex animal life on Earth. But it is short on stellar scales. Those 5 billion years are not a blank. There is a schedule. Over the next billion years, the Sun will gradually brighten. It is already about 30% brighter than it was when it formed 4.5 billion years ago. This gradual brightening is a consequence of the changing composition of the Sun's core. As hydrogen fuses to helium, the core becomes denser and hotter, the nuclear reaction rate increases, and the luminosity rises. In about 1 billion years, the Sun will be roughly 10% brighter than today. That increase will raise Earth's surface temperature enough to begin the runaway evaporation of the oceans, a slow, irreversible process that will eventually strip Earth of its water and its atmosphere. Life on Earth's surface, as we know it, has a finite tenure measured in hundreds of millions rather than billions of years. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core and begin to expand dramatically. The outer layers will puff outward as the internal radiation pressure from helium shell burning. forces the envelope to expand. The sun will become a red giant, growing to perhaps 200 times its current diameter. At maximum expansion, its photosphere will extend to roughly the orbit of Earth, possibly slightly beyond it. The inner planets will be consumed or scorched to bare rock. The outer solar system, Jupiter, Saturn, Uranus, Neptune, will survive, though their orbits will shift as the sun loses mass. After the red giant phase, the outer envelope will be expelled entirely, forming a planetary nebula, a glowing shell of gas expanding outward from the stellar remnant at speeds of tens of kilometers per second. Some of the most beautiful objects in the night sky are planetary nebulae: the Ring Nebula in Lyra, the Cat's Eye Nebula in Draco, the Helix Nebula in Aquarius. These are the death shrouds of stars like the sun, briefly illuminated by the ultraviolet radiation of the hot stellar core before fading over tens of thousands of years. What remains at the center of the planetary nebula is a white dwarf, a dense, compact sphere about the size of Earth, but with roughly half the mass of the sun. The white dwarf is not burning anything. It is the inert, degenerate core of the star, carbon and oxygen nuclei packed by electron degeneracy pressure into a solid crystalline lattice, still hot from the energy of its past, but no longer generating new energy. It will cool over billions of years, dimming from white to yellow to orange to red, until it is too cold to emit visible light. The sun will become a white dwarf approximately 5 to 6 billion years from now and will remain one for longer than the current age of the universe. But the sun's story cannot be told in isolation because the sun does not orbit alone and the galaxy it inhabits is not static. The Milky Way is moving, it is interacting, and its most significant gravitational relationship, the one that will ultimately determine its fate, is with the galaxy known as Andromeda. Andromeda, formerly designated M31, is the nearest large galaxy to the Milky Way, located approximately 2.5 million light years away in the constellation Andromeda. It is a spiral galaxy somewhat larger than the Milky Way, with perhaps 1 trillion stars to our 300 billion. It is approaching us. This is not a coincidence of current positioning. The Milky Way and Andromeda formed together, part of the same large-scale density fluctuation in the early universe, and they have been gravitationally bound to each other for most of their history, even as the expansion of the universe separated them briefly in the early universe before their mutual gravity overcame the expansion and began pulling them back together. Current measurements, based on the proper motion of Andromeda's stars, measured by the Hubble Space Telescope and subsequently the Gaia satellite, provide the most precise determination yet of Andromeda's trajectory. Gaia, launched by the European Space Agency in 2013, measures the positions of roughly 1 billion stars in the Milky Way with such precision that it can detect tiny shifts in apparent position caused by the proper motion of stars, their actual movement across the sky over years, down to micro-arcsecond precision. Applied to the stars of Andromeda, this precision allows measurement of the galaxy's transverse motion, its sideways velocity relative to us, with uncertainty of only a few tens of kilometers per second. The result from Gaia confirms what earlier Hubble measurements suggested. Andromeda is approaching us nearly head-on. The sideways velocity is small relative to the directly approaching component, meaning the collision geometry is essentially frontal. The expected first close approach in about 4 to 5 billion years is well constrained. What the simulations of this collision reveal is a richly complex sequence. The first approach will not be a clean merger. The two galaxies will interpenetrate, their stars streaming through each other's disks. Again, not colliding individually, but gravitationally disturbing each other's orbits. The tidal forces during the first close approach will draw long streamers of stars and gas out of both galaxies, visible as tidal tails in deep images. Observers at a great distance watching through telescopes would see the system as a classic interacting galaxy pair, the same kind of system visible in Hubble images of distant galaxy pairs where tidal distortions are clearly visible. After the first approach, the two nuclei will separate again briefly as they overshoot. Then gravity pulls them back together. Over several billion years of repeated approach and retreat, the orbital energy of the two galactic nuclei is dissipated, partly into the star systems disturbed by tidal forces, partly into gas heated by the star formation, burst triggered by the collision. The nuclei spiral inward. The two central supermassive black holes will each sit at the center of their respective stellar remnants for most of this time. As the remnants merge, the two black holes will eventually come close enough to form a bound binary system, two massive black holes orbiting each other. The final merger of the two black holes will occur when gravitational wave emission carries away enough orbital energy to bring them together. The resulting burst of gravitational waves will be detectable, in principle, from anywhere in the observable universe, but there will be no human civilization to detect it. Current measurements, based on the proper motion of Andromeda's stars measured by the Hubble Space Telescope and subsequently the Gaia mission, indicate that Andromeda is approaching the Milky Way at roughly 110 kilometers per second directly toward us, with a sideways velocity component that is relatively small. The collision is therefore essentially a head-on approach. The expected timeline is as follows. In approximately 4.5 billion years, the two galaxies will have their first close approach and begin to interpenetrate. The disks will pass through each other, their stars streaming past each other, because the average distance between stars is so large that actual stellar collisions are essentially impossible. In a galaxy containing 300 billion stars spread over a disk 100,000 light years across, the probability of any two stars colliding during a galactic merger is negligibly small. But the gas clouds will collide. Gas clouds interact electromagnetically. They can collide, shock, compress, and fragment. The merger of the Milky Way and Andromeda will trigger an enormous burst of star formation as gas clouds from both galaxies collide and compress, much as happens in the merging galaxies visible in deep telescope images. Brilliant blue clusters of newly formed massive stars will blaze across the merged system, burning hot and dying young. After the first close approach, the remnants will separate briefly, then fall back together. Over the course of roughly 3 to 4 billion years of repeated gravitational interaction, the two spiral structures will be completely disrupted. The spiral arms will unwind. The flat disks will be replaced by a roughly spheroidal distribution of stars. The two galactic nuclei will spiral toward each other as gravitational radiation carries away energy, and the two central supermassive black holes, Sagittarius A star at 4 million solar masses and Andromeda's central black hole at 100 million solar masses, will eventually merge in a catastrophic event that will release an enormous burst of gravitational waves. The merger product is expected to be an elliptical galaxy, a smooth, featureless, egg-shaped distribution of old stars with little remaining gas and almost no star formation. Astronomers sometimes call this future object Milkomeda. By the time the merger is complete, roughly 7 to 8 billion years from now, the Sun will already be a white dwarf, and Earth will be a scorched, airless remnant in the outer reaches of what used to be the solar system. What will the sky look like during the merger? This is a question that simulations can answer with some confidence. As Andromeda approaches over the next few billion years, it will gradually brighten in the sky. About 3.5 billion years from now, Andromeda will subtend an angle several times larger than the full moon, its disk visible to the naked eye as a faint oval in the sky. As the close approach begins, the Milky Way's own disk will become distorted, its spiral arms stretched and warped by Andromeda's gravity. The night sky will be ablaze with the light of newly formed massive stars, brilliant blue supergiants burning for a few million years before dying in supernovae. No human eye will see this, of course. The Earth as a habitable world will be gone long before the merger reaches its dramatic phase. But let us step even further back, because the fate of individual stars and even galaxies is embedded in a larger context that we have not yet addressed. The Milky Way and Andromeda do not exist alone. They are part of a structure called the Local Group, a collection of roughly 80 galaxies, most of them dwarf systems held together by their collective gravity within a region roughly 10 million light years across. Beyond the local group, the nearest significant galaxy cluster is the Virgo cluster. But the true significance of this cosmic neighborhood requires understanding the gravitational hierarchy that connects them. The local group sits in the outskirts of the Virgo supercluster, a loose aggregation of galaxy groups and clusters spanning roughly 100 million light years, first identified by Gerard de Vaucouleurs in the 1950s. The Virgo supercluster is not gravitationally bound as a whole. Dark energy is carrying its outer regions apart faster than gravity can hold them together. Only the inner cores of the supercluster, where the galaxy density is highest, are gravitationally bound. The discovery that the Virgo supercluster is itself embedded within a much larger structure called Laniakea came from a different kind of measurement. Rather than simply mapping where galaxies are, Brent Tully and colleagues in 2014 mapped how galaxies move. Specifically, the small deviations from pure Hubble flow caused by the gravitational influence of nearby density concentrations. Every galaxy in the universe is moving away from every other galaxy due to cosmic expansion, but superimposed on this expansion are small peculiar velocities, additional motions caused by local gravitational pulls. By mapping these peculiar velocities across the local universe, Tully and colleagues identified the basins of attraction, regions where peculiar velocities converge rather than diverge, indicating that galaxies in those regions are being pulled toward a common gravitational center. One such basin encompasses a region about 500 million light years across and includes the Milky Way, the Virgo cluster, and thousands of other galaxies, all showing convergent peculiar velocities toward a region called the Great Attractor, located about 150 million light years away in the direction of Centaurus. Tully and colleagues named this entire convergence basin Laniakea. The Milky Way is on the outer edge of Laniakea, moving toward its attractor along with its neighbors. But this motion will never complete. Dark energy's acceleration will eventually overcome the gravitational pull, and the Milky Way will not reach the Great Attractor. The motion is a relic of a past when the universe was decelerating, when gravity could still influence matter on these scales. Now, dark energy is winning. Beyond the local group, the nearest significant galaxy cluster is the Virgo cluster, approximately 54 million light years away. The Virgo cluster contains more than 1,300 known galaxies, including the giant elliptical M87, whose central black hole is 6.5 billion solar masses, the first black hole ever directly imaged by the Event Horizon Telescope in 2019. The Milky Way, the local group, and the Virgo cluster are all part of a larger supercluster called Laniakea, a Hawaiian word meaning immeasurable heaven, identified in 2014 by Brent Tully and colleagues using the velocities of nearby galaxies converging toward common attractors. Laniakea spans about 500 million light years and contains the mass of roughly 100 million billion suns. It is one of perhaps 10 million superclusters in the observable universe. But here is where the perspective becomes truly disorienting. Laniakea is not gravitationally bound. It is not a permanent structure. The parts of Laniakea outside the local group and a few nearby clusters are already being carried apart by the expansion of the universe, driven by dark energy, and will eventually be out of causal contact with us. The Milky Way's gravitational future is limited to the local group. Everything beyond that, the Virgo cluster, the larger structure of Laniakea, is already, in a deep physical sense, lost. The expansion of the universe is accelerating. The force responsible is called dark energy, and it makes up approximately 68% of the total mass energy content of the universe, compared to about 5% for ordinary matter and 27% for dark matter. Dark energy is modeled as a constant energy density of empty space, a property of the vacuum itself that drives the expansion of the universe to accelerate rather than decelerate. Its nature is entirely unknown. The consequence for the long-term future is this. Over the next 100 billion years, the expansion will carry every galaxy cluster beyond the local group, beyond our observable horizon. The sky for any future civilization still existing in the Milky Way Andromeda merger product will gradually empty of galaxies. The cosmic microwave background will be redshifted to wavelengths that would require a radio telescope the size of the solar system to detect. The evidence for the Big Bang, for the universe's beginning, for the vast structure of the cosmic web will become effectively inaccessible. A civilization arising in the local group 1 trillion years from now, starting from scratch, would have essentially no observational evidence for the Big Bang or for the cosmic web. They would see one galaxy, their own, surrounded by apparent emptiness. They might conclude that the universe consists of a single galaxy, that there is no expansion, that there was no beginning. All the evidence we have worked so hard to gather is specific to this epoch in cosmic history. This window of observational access to the full universe is temporary, and it is open now. Which brings us to the question of what we actually know about where we live and what it means to know it. And to appreciate that question fully, we need to acknowledge how recently we came to know any of it. As recently as 1924, it was scientifically controversial whether the Milky Way was the entire universe. Spiral nebulae, the fuzzy spiral objects visible in telescopes, might have been gas clouds within the Milky Way, or they might have been separate galaxies comparable to it in size and at enormous distances. The debate was settled when Hubble measured the distance to the Andromeda galaxy and found it was not a gas cloud, but a galaxy at roughly 900,000 light years, an underestimate but correct in order of magnitude. The universe expanded overnight from the Milky Way to something containing hundreds of billions of galaxies. As recently as 1978, the dark matter halo of the Milky Way was not established fact. It was a controversial inference from anomalous rotation curves that most of the community was still reluctant to accept. The idea that 80% of the galaxy's mass was invisible and undetected would have seemed extraordinary speculation to most astronomers of the previous generation. As recently as 2010, no one knew about the Fermi bubbles. The Galactic Center's past episode of intense activity, leaving its signature in gamma rays across millions of light years, was an unknown unknown. As recently as 2012, no spacecraft had ever left the solar system. Voyager 1's crossing of the heliopause, the boundary between solar wind dominance and interstellar medium dominance, gave us our first in situ measurement of the very edge of the sun's influence. The picture keeps sharpening. Gaia has transformed our understanding of the stellar halo and the galaxy's merger history. The Event Horizon Telescope has given us a direct image of the Event Horizon shadow of Sagittarius A star. DESI is mapping the universe's large-scale structure with unprecedented precision. The James Webb Space Telescope is observing galaxies as they appeared when the universe was less than 300 million years old. Which brings us to the question of what we actually know about where we live and what it means to know it. The Milky Way is a barred spiral galaxy. This was not confirmed until the 1990s because our position inside the disk makes it extremely difficult to observe the overall structure. We are like a fish trying to describe the shape of the ocean from the inside. The bar is a linear structure of stars extending through the central bulge, oriented at roughly 44 degrees to the line connecting the Sun to the galactic center. Its length is approximately 27,000 light years. As stars and gas follow elongated orbits aligned with the bar, reinforcing its structure through collective gravitational organization. The bar rotates as a rigid body, all parts of it rotating at the same angular speed, at a rate called the pattern speed, which is different from the orbital speed of individual stars. The existence of the bar was inferred before it was directly observed through the kinematics of gas in the inner galaxy. Radio observations of the 21-centimeter emission line from neutral hydrogen revealed gas moving in ways inconsistent with simple circular orbits, evidence of the elongated, non-circular orbits that a galactic bar would produce. Infrared surveys that can see through the dust of the inner galaxy, particularly the COBE satellite's galactic maps from the early 1990s and later the Spitzer Space Telescope, showed the bar directly as an asymmetric concentration of old stars in the bulge. The bar matters for the broader structure of the galaxy because it serves as a funnel for gas. Gas in the outer galaxy can lose angular momentum through interactions with the bar's gravitational potential and fall inward along the bar toward the galactic center. This gas inflow may be responsible for episodic bursts of star formation in the galactic center and may contribute to the growth of the central black hole by feeding gas into its immediate vicinity. There is also evidence that the bar is associated with the galactic long bar, a more extended structure connecting to the short bar in the central bulge and potentially extending outward toward the spiral arms. The full structure of the inner galaxy is still being mapped, with ongoing surveys adding new detail. The Milky Way is a barred spiral galaxy. The bar is a linear structure of stars through the central bulge, visible in long wavelength infrared images from which the spiral arms emerge. It contains between 200 billion and 400 billion stars, most of them red dwarfs. It has a diameter of roughly 100,000 light years and a total mass, including dark matter, of roughly 1 to 2 trillion solar masses. At its center is a supermassive black hole of 4 million solar masses. Its disk is embedded in a dark matter halo 3 times its visible diameter. The Sun is one of these stars. It lives in a minor spiral arm about 26,000 light years from the center, roughly halfway out from the galactic center to the edge of the visible disk. It has orbited the galaxy about 20 times. It will continue orbiting for another 5 billion years before evolving off the main sequence. Around the Sun orbit 8 planets, but the solar system's formation was not an isolated event. It was one of many star-forming episodes that built up the disk of the Milky Way from the gradual accretion of gas over billions of years. And the galaxy itself was built by mergers. The Milky Way has consumed other galaxies throughout its history. The evidence is preserved in the stellar halo, the sparse, roughly spherical cloud of old stars that surrounds the disk on all sides. Many of these stars have orbits that are misaligned with the disk's rotation. They are on elliptical, inclined, or even retrograde orbits, suggesting they were captured from external galaxies rather than formed in the disk. The Sagittarius dwarf galaxy, currently in the process of being torn apart by the Milky Way's gravity, has been orbiting and being slowly cannibalized for billions of years. Its stars are being stretched into a long tidal stream that wraps around the sky. Gaia has revealed the stellar halo in unprecedented detail. The orbits of millions of individual halo stars, precisely measured, show distinct groupings, stars with similar energies, angular momenta, and chemical compositions that were clearly once part of the same accreted galaxy. One of the most significant of these structures, identified in 2018, is called the Gaia Enceladus or Gaia Sausage Merger event, the debris of a galaxy about a quarter the mass of the Milky Way that merged with it roughly 8 to 10 billion years ago. This event was significant enough to heat and puff up the early disk, and may have triggered an intense burst of star formation in the early Milky Way as gas from the infalling galaxy compressed and fragmented. The Milky Way we inhabit is therefore not a pristine structure that formed in isolation. It is a composite, a galactic palimpsest written over with the remains of smaller galaxies it has absorbed over 10 billion years, their stars now scattered through the halo, their chemical signatures still readable in the compositions of the stars they left behind. Around the Sun orbit 8 planets, dozens of moons, millions of asteroids, and billions of comets. On the third planet, at a distance of 1 astronomical unit, 150 million kilometers, life arose about 4 billion years ago. It evolved through single-celled organisms, multicellular life, vertebrates, mammals, primates, and eventually a species that developed language, writing, mathematics, and telescopes. That species, which happens to be us, has in the last few centuries determined the size of the galaxy, the distance to its nearest neighbors, the existence of dark matter and dark energy, the age of the universe, and the fact that the universe began in a hot, dense state approximately 13.8 billion years ago. This is not a small accomplishment. Think carefully about what it required. We are embedded inside the galaxy we study. We cannot step outside it to see its shape. We are like cartographers trying to map a continent from a single city in its interior, unable to fly above it or sail around it. We can only measure what we can observe from here. And yet we have worked out that the Milky Way is a barred spiral galaxy with a diameter of 100,000 light years. We have measured the distance to its center to within a few percent accuracy. We have detected and characterized the supermassive black hole at its center by tracking the orbits of individual stars over decades with adaptive optics. We have inferred the existence of the dark matter halo through the rotation curves of stars we can see. We have mapped the spiral arm structure through radio observations of molecular gas. We have traced the chemical enrichment history of the galaxy through the compositions of its oldest stars. We have determined the galaxy's age by dating those oldest stars. We have tracked the positions of nearby stars within enough precision to predict orbital trajectories and identify exoplanets orbiting them. The techniques are diverse. Radio telescopes map the neutral hydrogen that traces spiral arms. Infrared telescopes penetrate the dust that blocks visible light, revealing the structure of the bulge and bar. X-ray satellites detect the hot gas and energetic processes in the galactic center region. Gamma-ray telescopes detect the Fermi bubbles, enormous lobes of gamma-ray emitting gas extending 25,000 light-years above and below the galactic plane, apparently created by past activity from the central black hole. Gravitational wave detectors have opened an entirely new observational window, providing information about compact object mergers that no electromagnetic telescope can see. Each technique sees a different component of the galaxy. The galaxy is a superposition of many structures, each transparent to some wavelengths and opaque to others, each tracing different physical processes. The complete picture requires assembling all these wavelength windows simultaneously. This is not a small accomplishment. The universe is approximately 93 billion light years across. The observable portion contains 2 trillion galaxies, most of them unreachable in any practical sense. The entire history of human civilization is roughly 10,000 years, less than 1/10 millionth of the age of the universe. In that 10,000 years, and particularly in the last few hundred, we have managed to reconstruct the history of a universe that began before we existed and will continue long after we are gone. We have done this from one planet, around one star, in one arm of one galaxy. The achievement is built on centuries of accumulated observation and theory. Galileo first resolved the Milky Way into individual stars with a telescope in 1610. William Herschel attempted the first systematic map in the late 1700s. Harlow Shapley placed the sun correctly off-center from the galactic center in 1918. Edwin Hubble proved that the spiral nebulae were separate galaxies in 1924. Jan Oort measured the rotation of the Milky Way and helped determine the sun's distance from the center in the 1920s. Grote Ribber built the first radio telescope and detected radio emission from the galactic center in 1943. Hendrik van de Hulst predicted in 1944 that neutral hydrogen would emit at 21 centimeters wavelength, and in 1951, Harold Ewan and Edward Purcell detected it, providing a tool to map the galaxy through the dust. Vera Rubin measured the flat rotation curves in the 1970s. Reinhard Genzel and Andrea Ghez tracked the orbits of stars around Sagittarius A star through the 1990s and 2000s. Each step built on the last. Each generation of astronomers inherited a partially completed picture and extended it further. The accumulation is not merely quantitative. More stars measured, more distances determined. It is qualitative, the framework for understanding what a galaxy is, what dark matter is, what the large-scale structure of the universe is. These frameworks changed completely within living memory, driven by new instruments, new techniques, and the willingness to follow observations to conclusions that contradicted previous assumptions. None of the scientists who made these discoveries knew in advance that they would find what they found. Herschel is expected to find the sun at the center. Rubin expected to confirm Keplerian decline. Perlmutter and Schmidt expected to confirm deceleration. The universe consistently revealed itself to be stranger than the models predicted, and the scientists consistent enough to follow the evidence ended up rewriting the models. The picture we have now is not the final picture. There are deep mysteries remaining, from the nature of dark matter to the detailed history of the galaxy's assembly, to the origin of the Fermi bubbles, to the mechanism of the first star formation. But it is a picture built from evidence, tested against independent measurements, and consistent across every scale we can probe. We have done this from one planet, around one star, in one arm of one galaxy. The Milky Way is our home. It is also, in the context of the observable universe, a single point among 2 trillion. It is a structure so large it would take Voyager 1.8 billion years to cross, and so densely built that you can see the light of 100 million of its stars with your naked eyes on a clear night. It contains the remains of stars that lived and died before the sun was born. It is currently being gravitationally drawn toward a collision that will restructure it beyond recognition in 5 billion years. It is embedded in a dark matter halo 5 times its own visible mass. And at its exact center, hidden by clouds of dust and gas, there is a black hole of 4 million solar masses around which stars orbit at 28 million kilometers per hour. We know all of this now. We have measured it, derived it, tested it against observations from radio telescopes and X-ray satellites and infrared interferometers and gravitational wave detectors. The picture is not complete. There is much we do not understand about dark matter, about how the spiral arms maintain themselves, about the history of the galactic merger events that brought the Milky Way to its current size. But the broad architecture is known. We live in a spiral galaxy, mid-sized by galactic standards. Let us be specific about what mid-sized means. The smallest known galaxies are dwarf spheroidals, tiny collections of a few million stars, some containing even fewer. The Sega 1 galaxy, one of the smallest known, contains perhaps a few 100,000 stars. The largest galaxies are giant ellipticals, smooth, featureless, roughly spherical collections of trillions of stars. IC 1101, one of the largest known galaxies, is estimated to contain about 100 trillion stars and has a diameter of roughly 6 million light years, 60 times the diameter of the Milky Way. The Milky Way, with 2 to 400 billion stars, sits comfortably in the middle of this distribution, not exceptional in either direction. About half of all stars in the universe reside in Milky Way-like galaxies, making the Milky Way a reasonably typical example of the most common type of large galaxy. This typicality is actually scientifically important. If the Milky Way were unusual in some way, the lessons we learn from it might not generalize to the broader galaxy population. The fact that it is typical means that what we learn here likely applies broadly. The Milky Way is also typical in its position within the large-scale structure of the universe. It is not in a very dense cluster like the Coma cluster, where galaxy interactions and mergers are frequent and where the hot intracluster gas strips spiral disks of their cold gas. Nor is it in an extreme void, where galaxies are isolated and evolved without significant external influence. The local group, with its two large spiral galaxies and dozens of smaller companions, is a moderately populated environment, representative of the kind of group in which perhaps a third of all galaxies reside. We live in a spiral galaxy, mid-sized by galactic standards, with a supermassive black hole at its center, a dark matter halo surrounding it, and 200 to 400 billion stars inside it, most of which will never be visited. We live on a planet around a middle-aged star in an outer spiral arm, about two-thirds of the way from the center to the edge. Step outside tonight if you can. Look up. The pale band stretching across the sky is the disk of the galaxy seen edge on from the inside. You are looking along the plane of the disk, past hundreds of millions of stars, whose light blends together into that diffuse glow. The direction you are facing when you look toward Sagittarius is the direction of the galactic center, 26,000 light years away, hidden behind clouds of dust, where 4 million solar masses of black hole sit in silence, occasionally disrupting the orbits of stars that stray too close. That direction is the center of your galaxy. Turn 180 degrees, and you are looking toward the outer edge of the disks, the direction in which the stellar density gradually thins, the spiral arms become sparser, and eventually the disk gives way to the halo. In that direction, the stars visible to the naked eye are still mostly within a few thousand light years of you. The far edge of the disk is 50,000 light years away. There is nothing to see there with the naked eye except the faint background of the sky. Look perpendicular to the galactic plane, straight up or straight down relative to the disk, and the stars thin quickly. You are looking out of the disk into the halo. In that direction, a few thousand light years away, the stellar density drops to near zero, and beyond the halo is intergalactic space, the void between the Milky Way and its nearest neighbors. The Magellanic Clouds, the two small irregular galaxies that orbit the Milky Way and are visible from the southern hemisphere as separate patches of pale light, are in this direction, about 160,000 and 200,000 light years away, respectively. Every star you can see with the naked eye is in the Milky Way, every single one. The most distant individual star visible without a telescope, a blue supergiant in Cassiopeia called V762 Cass, is about 16,000 light-years away. The Andromeda Galaxy, the most distant object visible to the naked eye under ideal conditions, is a faint smudge about 2.5 million light-years away. Everything else in the night sky is between your eyelid and Andromeda. You are embedded in a structure containing 2 to 400 billion stars, most of which you cannot see, most of which have never been named or cataloged, most of which will never be visited. The Sun is one star among 300 billion, a middle-aged G-type main sequence star at an unremarkable address in an outer spiral arm. And yet, from this unremarkable address, looking with eyes that evolved to track prey on an African savanna 65,000 years ago, adapted for instruments of glass and metal and silicon, we have measured the galaxy, found its center, characterized its black hole, discovered its invisible halo, predicted its collision with Andromeda, and traced our own chemical ancestry back through generations of stellar explosions to the first 3 minutes of the universe. Step outside tonight if you can. Look up. The pale band stretching across the sky is the disk of the galaxy seen edge on from the inside. You are looking along the plane of the disk, past hundreds of millions of stars whose light blends together into that diffuse glow. To the south, in the direction of the constellation Sagittarius, lies the galactic center, hidden behind 26,000 light-years of dust. 4 million solar masses waits there, invisible. You are looking at 1% of the stars in your galaxy. The rest are behind you, above you, below you, in directions you cannot see. You are surrounded by 300 billion stars in a disk 100,000 light-years across. And beyond the disk, extending 3 times as far in every direction, is the dark matter halo, invisible, massive, holding everything together. That pale glow is your home, and now you know what it is.